Greetings in the love and light of the infinite creator. I am Andrii, and joined here with Doone, Ivor, and Roger, and Barbara. And today we will be discussing deep geothermal. Also, we're hoping to get some more people in attendance later. But first, I'm going to start with a brief overview of the state of geothermal, and then we'll get into Doone's presentation. So if we just have a quick look here. So geothermal, globally, deep geothermal electricity stands at 17 gigawatts installed, producing 98 terawatts hours per year. That's 0.35% of global electricity generation. 5 countries produced over 70% of that power: United States, Indonesia, Philippines, Turkey, and New Zealand. Over the last decade, geothermal electricity has grown slowly at about 3% a year. Well, I think steadily would be the better term. Geothermal heat is much larger. Combined deep geothermal heat and shallow ground, 280 terawatt hours of heat per year globally. Installed thermal capacity over 100 gigawatts. 60% of that capacity is shallow geothermal heat pumps, which has grown to 9% per year. And the cost of deep geothermal electricity average is about 6 cents per kilowatt hour. And the big news, closed loop and enhanced geothermal ERoI technology connected to German project grid in late 2025. So they're finally, proven the technology, or at least they've started producing electricity. That project combines 8.2 megawatts of electricity with 60 megawatts of heat power. So they can reach payback within 15 to 20 years, or closer to 10 years when district heat is fully utilized. And then looking forward, global capacity could rise from the 17 gigawatts today to 120 gigawatts by 2035 and 600 to 800 gigawatts by 2050, producing 5,000 to 6,000 terawatt hours of electricity per year. On the heat side, 10,000 petajoules per year, or 2,800 terawatt hours of heat. All right, over to you, Doone. Okay, did you want to introduce yourself, and then we'll start your presentation?
Sure. My name's Doone Wyborn. I worked in the geothermal industry for about 20 years, initially doing research into what's called hot dry rock geothermal energy. So a brief idea about what that means is that standard geothermal is generally done in volcanic areas, and production is through just drilling one hole at minimum. With hot dry rock, it was actually initially developed by the Los Alamos National Laboratory in the very late 1970s. And the idea is that you don't need to have water present in the rock. You drill at least 2 drill holes, and you pump water down one hole, and it comes up a second hole and passes through the rock in some way, and then comes back heated. So the Los Alamos project was developed at Fenton Hill, and just out of Los Alamos, a few kilometers out, and that was kind of the forerunner of quite a lot of other projects, including one that I started working on in about 2002. And the company that was formed around our project, it was called Geodynamics. We developed this project in a totally non-volcanic area where there was sort of geological conditions. I'm a geologist, by the way. Can you see me?
Yeah, there.
Yeah.
I fixed it. Okay.
Yeah.
Mm-hmm.
So we developed this project in an area where we were claiming that had the highest temperature gradient in the world in a non-volcanic region. It turned out that was in the middle of Australia, in the middle of nowhere, where there is virtually no call for energy use. But that didn't stop us.
Okay.
And so we worked on this project for 10 years, and we ended up creating what's called a reservoir an artificially enhanced reservoir, which was also done in the other projects that were going on at that time, and it's done by what we call stimulation, but it's essentially like fracking in the oil industry. So we created what's still regarded, or still is, the largest fracked reservoir in the world in our project in Central Australia, and I'll show a few slides about that.
Okay, sure.
So that's my introduction.
Thanks. I can get your slides up now. So you just need to click on your presentation there. Okay, and now you can go into presentation mode. There. Okay, we can see it.
You see that?
Yeah, and you could move that meet little window a little to the side.
Okay.
So yeah. Okay, there you go. Okay.
Yeah.
Very good.
So Andrii introduced you to how much energy has been produced by what he called deep geothermal, but what I'm going to be talking about tonight is not actually deep geothermal in the sense of volcanic geothermal. This is potentially geothermal that can be produced anywhere in the world, as long as we can drill deep enough. And the advent of new drilling technologies and faster drilling speeds means that potentially sometime in the future, this kind of geothermal may well be able to be utilized. And I'll just briefly go through what I've showed on the screen here. First of all, we now call enhanced geothermal systems, is actually what the Los Alamos team called hot, dry rock in the early days, in the 1970s and early 80s. So enhanced geothermal systems has actually taken over as the term for that kind of extraction of heat out of the earth. I'll just briefly indicate some new drilling technologies that have allowed drilling to take place, or shown that we can now drill much, much faster than we used to be able to drill, like back 10 years ago when I was working on it. And the projects, Andrii mentioned the EVA project in Germany. Well, there's a couple of other projects that are happening as well. And what I really want to do tonight, though, or today, is to introduce you to a whole new significance of deep geothermal that may well actually be our savior. And that is that if you drill deep enough, you actually enter what's called the brittle ductile transition. And there's quite a bit of evidence in a few places, and theoretical evidence, that this area has much higher fluid permeability than the rest of the crust, the Earth's crust. So if you can actually drill to the brittle ductile transition, and I'll talk about what that is later, it may well be possible that we can generate lots and lots of power anywhere in the world if we can drill deep enough. And the data that I'm going to show is the data that comes from our own project in Central Australia at a place called Inaminka. My company's name is Geodynamics. So I want to show you data that came from that. This is unpublished information that that hasn't been shown before, and plus information from Iceland. So hopefully,
did you want to go to the next slide?
Yeah, you're the one who has to transition, are you?
Oh, no, you are. They're on your end. You're the.
I'm not sure how to transition in this condition.
Oh, can you not see your presentation?
I can see it.
Can you click on it?
Oh yeah, click on it.
There
Yes,
you go.
yeah, here we go. Sorry, I can't.
Try to keep
not
it
sure
like.
whether I can go. Oh yes, I can go backwards. Yep. Now I'm right.
Yeah. Okay.
Yeah. So this is just a kind of a picture of what EGS, enhanced geothermal systems, look like. You basically have two or more wells. You pump cold water down one well, and it comes up another well hot, and the water goes through the rock between the two. Somehow it's got to get from one to the other. And this is typically thought of to take place at maybe up to 5 kilometers depth, and with rock temperatures of about 250 degrees. So the word fracturing or fracking is required to actually enhance the permeability of the rock between the two wells. And that's done similar to shale oil fracking or oil shale fracking. And it's been quite successful in the projects that were carried out, but it's kind of expensive, and the flow rates between the wells have not been all that crash hot. So it hasn't actually really, up until now, become economic.
Okay.
This is just quite a few projects are now happening in the USA, and in particular, the project in Utah called Cape by a company called Fervo. I'll show you some information about that in a minute. The oldest one was the Fenton Hill one in New Mexico. That was in the late 70s. So there's quite a lot of work going on in the USA, and there's a lot of work going on in Europe. The most important part is on the French-German border in the Rhine-Graben, and these are some of the projects that are actually happening. But you can see that the energy being produced in these projects is pretty small, like 3-4 megawatts, and that's electrical. This one is 24 megawatts thermal, but no electricity, because it's just not hot enough. In the Rhine-Graben, you've got to drill a long way down to get to temperatures that are high enough to generate electricity. One of the critical things about this is that the hotter it is, it's kind of like a scale of that's exponential in terms of temperature. So if you can get to really high temperatures, and I'm talking about 350 degrees instead of 250 degrees, you can generate like 10 times more power with the same flow rate. The other project that's there's been projects in Japan. A couple of projects have been carried out in Japan of this EGS or hot dry rock work, and they were somewhat successful. They were able to circulate water and show that it can be done. But I want to talk particularly about our project at Inaminka in Central Australia in this talk. This is the Cape Station project in Utah. What happened here is at a place called Blundell, there is a normal wet geothermal project generating electricity at Blundell.
Okay.
The US government, Department of Energy, started a research project at Forge, a little bit away from there. And what they were able to do, this is granite in this area here.
Okay.
They were able to drill some inclined wells, and this is all with government money, and actually prove that it works. And
this is the Utah Forge?
Sorry?
This is the Utah Forge, people?
Yeah, that's it. Yeah,
okay,
Forge.
Cool.
Forge was funded by the Department of Energy, US Department of Energy.
Yeah. And this is depth in feet. Okay.
And they kind of proved it was going to work there. But this is where the permeability of the rock is very low, and so they needed to do this fracking or stimulation to get water between the two wells, the two inclined wells.
Yeah.
So on that basis, Fervo, a company, decided that they would move further away and still work in this impermeable granite basement, and drill horizontal wells. So they drilled down about, well, it's 9,000 feet, and horizontally about 4,000 feet, or down 4 kilometers and horizontally
So
3
that's
kilometers.
2.74 kilometers deep, 9,000 feet.
Yeah, and horizontally. And they've been able to create a reservoir there, which they are now working on to make commercial. So that's really the first commercial project that's now happening in EGS. Before they did that, they worked in Nevada on their Project Red, and in the same situation, they drilled horizontal wells and they fracked between the wells. So that's where they got their first sort of expertise in doing this. You'll notice in this picture that the fracture planes are kind of vertically oriented between the wells. And that's why they have to drill horizontally to join the wells together in fractures which run vertically. They in order to do multiple fractures between the wells, they have to do they have to kind of separate parts of the well from one another and frack them individually. It's a lot of work, and it's but nevertheless they've achieved it, and they've achieved it in Utah as well. This is this is the project at Red in Nevada, and you can see here a whole lot of dots. These dots are actually microseismic events or micro earthquakes, and during the fracking process, if they've got a network of seismic monitors, they can locate where the water is actually passing, and you can see that there are a number of separate places where they've fracked individually in different locations. And the microseismic monitoring process is something that's been done in every one of these projects, including Los Alamos back in the late 70s. So it's all about creating micro earthquakes so that you can see where the water's going and where you can target your production well if you're fracking from an injection well.
Oh, and I see we have Dan joining us here, and he knows about drilling and fracking as well.
Yeah, good day, Dan. Good to see you. Probably more importantly is the fact that these projects, like in Project Red, this is a graph of the number of days it takes to drill a hole versus the depth. And you can see that now we've in the Fervo project at Cape, they're drilling holes to 4,000 meters in 20 days. Well, I can tell you that is absolutely amazing. And also, since a lot of that drilling is in granite, it's pretty hard to drill in granite, but with new technologies, you can drill to 4,000 meters in 20 days. When we were drilling our wells in the early 2000s, it took us 100 days to drill to 4,000 meters. So that's how much improvement there's been.
Can you tell us what these new technologies are that allow it to go so much faster?
I don't really know, other than an improvement in the drill bits, diamond drill bits. The technique has been the same as what has been going on for a long while. We had these diamond impregnated drill bits, just like they have now. This is what they look like, diamond composite bits. But I understand that these things have been improved a lot, and so they can drill a lot faster and a lot further without changing bits. So these are some of the bits that they used in the Cape project. There are other new technologies, and I've just before I go to that, this is the project that Andrii mentioned in Germany, where they drill an injection well and a production well, and rather than fracking, they actually are able to connect the two wells together, and so that they're flowing water just around the wells, an injection well and a production well, and then they make multiple well pairs and extract the heat out that way.
And they start
pretty expensive and not economic, but
it is
going ahead and doing it.
Well, actually, the economics works out fine. Like the project pays for itself within about 10 to 20 years, and they actually started delivering power in December.
Yeah. Yeah, 10 to 20 years is not good economics for somebody trying to make money, but it may be of value when we've got no other way of generating electricity.
Fair
yeah.
enough. It also allows us to go deeper than 4 kilometers.
Sorry?
This is the first successful deep geothermal project that's deeper than 4 kilometers.
Yeah. They went down 4 kilometers and then horizontally 3 kilometers. So that's a lot of drilling.
It's the deepest one so far that's successful.
Yeah. So I don't know what techniques they were using for drilling, whether they were just using diamond composite bits and standard techniques, but there are other technologies that are being developed that don't have drill bits that actually grind the rock away, but this is one of them, millimeter wave drilling. It's thought that it'll be much faster and you can drill much deeper because you're actually using electrical. I think they use this thing called a gyrotron to break the rock apart. And there are other ways like quench drilling and thermal sporulation drilling, which are being researched. The whole point of this is that if we can drill faster, we can make it economic. So the important part of this talk that I'd like to give is about the potential for rock permeability at the brittle ductile transition. And if we can drill to this depth and we find that the rock is permeable enough, then we may be able to forego the whole idea of fracking and also drilling horizontal wells. And I want to go through this in some detail to indicate that this could be a game changer for deep geothermal. So what is the brittle ductile transition? As you go deeper in the rock changes from being brittle and breaking on fracture planes to being ductile, where it kind of flows rather than breaks. Of course, if you apply enough stress or differential stress to a ductile rock, then it'll break as well. And so you do get earthquakes in ductile rocks. However, in the kind of stresses that are going on in the earth in normal conditions, this brittle ductile transition occurs in rocks with a lot of quartz, such as granite, at around about 400 degrees C, and in rocks that are made of basalt, where there's no quartz present in the rock, it's up to 700 degrees C. So if you were to drill down deep enough anywhere in the earth, you'll get to 700 degrees C. But more importantly, in continental areas, we're going to be trying to get to 400 degrees C or thereabouts. And also, very importantly, water becomes supercritical at about 400 degrees C. So its density, it's neither gas nor liquid. Supercritical water occurs at 374 degrees C, and the density of supercritical water is only 0.3 of that of water. And this means that water can actually pass, or the permeability of the rock with supercritical water is much higher, and water can pass through the rock almost on a grain boundary scale rather than along fractures. And that's what makes the brittle ductile transition potentially very important. And if we can drill to that temperature, then potentially we can get the heat out a lot easier than doing all the fracking and having multiple wells, injection and production wells. So just to go on from there, I'll now want to talk about my project back in the early 2000s. This is a map of Australia showing the estimated temperature of the rock at 5 kilometers depth. And in this area around here, where we did our project, the highest temperatures were at a place where we estimate that the rock temperature was 300 degrees at 5 kilometers depth. So that's getting pretty shallow. And we claim that it's the hottest rocks in the world in a non-volcanic environment.
Mm-hmm.
And the reason for that is that there's a granite that's buried at about 3.5 kilometers depth. Now, the granite is defined here in a gravity map. So granite generally has a lower gravitational force than rocks that it surrounds, that surround it. And so this area here is about 1,000 square kilometers, is a large granite body. It had been drilled by oil and gas industry, and so we knew the granite was there. And also critically, this granite was what we call a high heat producing granite. It was high in uranium and thorium.
Oh, okay, that's why.
So, and the heat that's being given off from that granite is kind of being insulated by the blanket of sedimentary rocks, 3.5 kilometers of sedimentary rocks overlying it, and hence we get the high temperatures at that depth. So that was what guided us into doing our project in this area.
So it's kind of like nuclear, just through deep geothermal.
Yeah, well, that's right. The heat from the earth, a lot of that heat comes from radioactive decay, and a lot of it comes from the first coalescence of the earth like 4.5 billion years ago.
Mm-hmm.
So the heat that's coming out of the earth everywhere, about half of it's coming from radioactive decay.
Oh, wow. Mm-hmm. Mm-hmm.
Yeah, it's a lot. So this is zooming in on the area where we worked. We actually drilled it in 3 different areas, and we named the wells after hot chili peppers.
That's funny.
And they were 10 kilometers apart, these 3 wells: Habanero, Jolokia, and Savina. And Habanero is where we developed a small project, and we built a power station and proved that it was all going to work there. But I showed you that picture of the red project in Nevada, where the fractures were vertically oriented. Well, one of the things that we had determined in this area was that the fractures in this area were going to be that would produce from stimulation with water were going to be horizontal rather than vertical. And that would mean that they would sort of spread out in a pancake kind of shape, and it would be a lot easier to drill into those fractures and extract the heat without actually drilling horizontal wells. And that was the basis of our projects in this area. And it actually turned out to be the case. And this is the results of our stimulation. And you can see here that we actually located something like 70,000 micro earthquakes. And you can see there located this as kind of a elevation showing the fractures extending sub-horizontally and then bending down and then heading downwards. And
so do you have seismic stations up on the surface?
Yeah, we had about 10 seismic stations in not just in the surface, but in drill holes down as deep as we drilled our own wells down to 100 meters. But there was also one drill hole that was drilled by the oil industry we had a seismic station down at 2.5 kilometers as well, which helped to locate the vertical orientation of the vertical location of the
I have heard that when you get hot enough so the rock is plastic, that it'll squish in and fill the hole with molten rock. What's the story about that?
That's right. That's definitely right. However, if like here the temperature is 250 degrees, we were the highest temperature we were to measure was 270 degrees at 4.9 kilometers.
So there's a Goldilocks temperature, hot enough to make a profit and cold enough so you don't fill in your holes with molten rock?
Yeah, well, not molten rock. It's a plastic flow occurs way before at much lower temperatures than molten rock.
Fluid rock or whatever it is.
Yeah, that's right. Yeah.
Well, wait a minute. I have heard that problem is enough to scotch the whole concept of producing electricity this way. Is that simply not true, or what?
Yeah, there's an argument about that's correct. However, I would like to be presenting in this talk some evidence that that we can get away with it at the brittle ductile transition. I don't know, Charlie, whether you were here when I first mentioned that earlier in the talk.
I came in a little bit late, so I guess I missed it. So anyway, I'd like you to cover that in a little bit of detail, if you would.
One of the kind of missing things from here is, do you know what pressure it was at that depth? Because basically, I don't know, it was like 100 megapascals, and at around that, we don't have anything to keep the fractures open, and so they reseal after a few weeks or hours, depending on how much pressure there is. I'm wondering how long these fractures stayed open.
These ones at this depth, they remain open all the time, but it's the pressures are not high enough to close them up, and the reason for that is that the fractures are actually rough on a grain scale size. So when you stimulate or when you create a micro earthquake, the rock moves a few millimeters and they remain open. Now, sure, if you just left the rock there without pumping water through it for maybe hundreds of thousands of years, then those spaces would actually fill up with silica. But on the time frames we're talking about here, they remain open for long enough to extract all the heat out, basically.
Oh, okay. Yeah, I guess it was the Finnish deep heat project. They were at 6 to 7 kilometers deep, and they found that as soon as they stopped the fracking, it would start resealing. But yeah, it was much higher pressures, and it was significantly deeper.
What do you know? What temperature it was? I don't know.
It was only 150 Celsius, but it was the pressure that was the problem. Everything was sealing in around. I don't know if Dan do you have some insights to share on this?
Well, as far as what you're talking about, the 30 some odd geothermal power plants we built that have been built out west, we keep the wells pressurized to keep the fracture network open. The other thing is we found out is once you drill past 10 kilometers, the rock itself is basically full of hydrogen and water, so it's not as quite as dense as what you would think. The crustal rock that's closer to the surface is actually denser than that rock, and the reason why is because it's become cold, hard, and brittle.
Yeah,
Dan,
this is where the
elemental hydrogen down
comes
there.
into play.
Yes. It runs between 16 and 18% hydrogen content.
Is that enough to exploit?
Probably. I've got some people talking about it right now.
Cool.
Yeah.
How to get there?
Well, I've got a presentation. We can talk about it. If I
Okay.
can get Andrii to basically wait until after I give the presentation, and then we can talk about those things.
Okay. Cool.
Well, I better move on quickly with this then.
Okay. All right. Go ahead.
So you can see here that the fractures that we stimulated, it turned out that these fractures were pre-existing and overpressured with water to the point where we had a lot of difficulty drilling them. And that overpressure came because of the high stresses within the rock. So you are talking about high stresses, and these fractures were pre-existing and open and full of high pressure water. And so we didn't have any trouble getting water out of these fractures. And what we ended up finding was that the fractures actually extended many kilometers, and they bend downwards and head down into the depths. So here, this is a plan view of the microseismic events, and that's essentially one planar surface of a fracture that we drilled into. This star here is the well that we pumped water down, and you can see here, I wanted to show here that this fracture plane dips to the northwest, and as we were stimulating, the coloring is the time of the event. And so as we were fracking, you can see towards the end of the project of the fracking that there are these little grey stars extending to the northwest up here, and also up here. And this is a little later, and you can see they're extending further to the northwest and west. And so these micro earthquakes were actually extending downwards, and the fracture was kind of terminated to the east or southeast, and the fracture plane or the stimulation was not extending any further east. So we took that as that the fracture was actually coming up from deeper down. And more importantly, during the stimulation, we had these what we call off-reservoir seismic events to the northwest, and our monitoring network was not close enough to actually accurately locate those off-reservoir events. They ended up being like 7 to 10 kilometers away from our, or if I go back to the scale here is in meters, so the reservoir itself is about 3 kilometers by 2 kilometers. And we had our seismic network around that area to accurately locate them. So these off-reservoir events happened. We had 23 events way off to the northwest, all in the one area while we were fracking. And this is an attempt at locating them using, there's the network of stations there. There were 2 networks, one for our Habanero network and the other for the other well that was 10 kilometers away for the Geologia network. And we know the direction of these off-reservoir events up this way, and this is an attempt to locate them depending on how far away they were. And it turns out that they occurred at the brittle ductile transition, essentially, which is down in our area around about 8 kilometers. So this to us indicated that this fracture that we'd actually discovered came up from the brittle ductile transition, and so that we then start looking at theoretical reasons why it did, and this is a paper that was published in Nature in 2006, which showed that the brittle ductile transition is actually is a weakness within the Earth, and there's likely to be movement and permeability potentially at that depth. The guys who did this, who published this paper, did some research on strain over time, sort of modeling, and this is what they came up with. They modeled essentially our geology with a large body of granite underneath, and the top of the granite at 3.5 kilometers depth, and they actually were able to theoretically produce fractures which came up from deeper levels up to the top of the granite with 2.5 million years of strain. So this is kind of what's made us look like we can actually potentially get water from the brittle ductile transition. And so this is kind of a little sketch of what might be the case. We've got a 20-kilometer distance between our 3 sets of wells. And importantly, when we drilled this well, the 4,900 meters, we didn't intersect any natural fractures. And even though we stimulated, we didn't create, it was very hard to actually move the rock. Whereas at this well and this well, we intersected a natural fracture, and that natural, at least for the habanero location, that fracture was coming up from deeper down. And we can imagine that the water that's coming out of that fracture was coming from deeper down. So one could think that instead of needing to drill down to 8,000 meters, that we can actually utilize the fracture itself as a pathway for fluid flow. So the possible project in the future is to, these wells are now abandoned, by the way. So a possible project is to drill back into this fracture, and we actually drilled into this fracture 4 times. We know exactly where it is, and flow from that fracture and see where the water comes from over time. That would mean that we could possibly prove one way or another that water was coming from greater depths. We've done analyses of chlorine isotopes of the water, and it shows that it's definitely water that comes from nature, not the water that we used to frack the well. And so you can imagine this is a kind of project that is possible. You have an injection field, you pass the water down through a fracture to the brittle ductile transition, up another fracture, and out a production field. This particular granite, which is a high heat producing granite, it's 1,000 square kilometers in area, and high heat producing granites are actually also high in lithium. And it turns out that this water that we were producing is very high in lithium, much higher than projects that are actually now, geothermal projects that are now being dualed into 2 sort of 2 lots of commercial output. One is the heat, and the other is getting the lithium out of them. Well, this project could take place here, and there is a small company that owns the lithium rights in this area, and they're working on trying to get money to drill another well. Now, if we go to Iceland, how am I going for time, Andrii? Can I keep going?
Well, I don't know. Could you finish within the next 5 to 10 minutes?
Yeah, easily. Yep.
Okay, cool.
Yep. So in Iceland, they drilled. When you get to high temperatures, it seems as though you can get high production rates, and because water is at supercritical conditions. So in the Iceland Deep Geothermal project, they drilled into a magma chamber, and just above that magma chamber, this is a place called Krafla. They produced water for 3 years continuously at 450 degrees C, and there was no reduction in wellhead pressure over the whole time. When they tried to produce to collect this water and build a power station, they actually damaged the well and they had to shut it in. And they have plans in their deep drilling project to work in other locations. So there is a plan to actually drill to temperatures where water is supercritical for geothermal output. In southern Iceland now, there were some natural earthquakes. Oh, these blue lines should be down here. They've moved. So the aftershocks from those natural earthquakes terminate at the brittle ductile transition, which in Iceland is at 10 kilometers or 8 to 10 kilometers, because it's in basalt, not in granite. So the brittle ductile transitions at 600 to 700 degrees C. They also did magnetotelluric studies, which measures the electrical conductivity of the rock, and down in this depth, electrical conductivity seems to be higher, again suggesting there's a high fluid porosity anyway around about the brittle ductile transition. So the bottom line is, this is where I can finish up now, there is a potential for high permeability at that depth in granites where the water is supercritical. We may only need to drill vertical wells to get to this depth, and we may not need to frack. And this is, whoops, why isn't that flowing?
That won't. Were you trying to show a video or something?
Yeah, I was trying to show a video. Yeah.
Yeah, I'm not sure this platform will work with the video.
Okay.
Yeah.
Right. Anyway, I'll show you the picture.
Okay, sure.
Sorry. View slide sorter. Yeah, this is basically flowing water at 250 degrees C at about 35 kilograms per second, and this is where you're basically flashing the steam to atmospheric, and it's pretty spectacular. All of that was driven by the fluid overpressures in the fracture. So, and all of this water is natural water from 4.5 kilometers down, and high in lithium. So that's the end of my presentation. Thank you, guys.
Cool. So questions from the panel? Anyone have questions for Doone? Roger, go ahead.
Thank you. Thank you, Doone. A very good presentation. Really very, very nice. Much appreciated. One is just simply a comment. As the other people on the panel know, Jean Herrera and I and Charlie have been working for years on global peak oil, which of course conventional oil peaked about 20 years ago, global conventional. When we went about 25 or 30 years ago to the Danish Geological Survey and told them that peak oil was coming along, they said, why worry? Pointed down underneath the table and said, look, beneath our feet is lots and lots of energy. So here we are, 25 or 30 years later, starting to see it. Very pleased. One technical question, please, Doone. When M.K. Hubbard, the geologist, helped to understand why rocks can bend and not frack, is that to do with the brittle ductile transition, or is that something completely different? I'm not sure I understand.
Hubbard said that. Yeah, I'm not sure.
Hey, Simon.
Hi there, Simon. I'm not sure what he was talking about, but yes, rocks flow when they get hot enough, and it depends on the mineralogy of when they flow, and of course the stresses, the differential stresses at a given point in the Earth. The stresses are different in different directions. There's a maximum, minimum, and an intermediate stress value at any point in the Earth. At our location, the minimum stress was vertical, and that meant fracking occurred horizontally. In many areas of the world, the minimum stress is somewhat horizontal, and so fractures occur oriented vertically. And that was the case in the Red project in Nevada, and also it's the case in most places.
Doone, anyway, thank you very kindly for an excellent presentation.
All right. And so I know there's... oh, Doone, could you stop sharing your screen?
How do I do that?
So you just click on the share screen button again.
Where is it?
it's in the bottom, the third button. Okay.
Just move your mouse. You'll see it.
Yeah.
Sorry. Oh, move my mouse.
Yeah. There. That's it. Okay, great. Okay, here. So there's a few questions from the audience. One of them is about water and I guess automatic circulation and pressure. I guess I've kind of answered them in the chat here, but we have a Wenceslaus. You're here with us. Would you like to ask your question? Okay. Well, anyways, I'm not sure I really understand his question. It might be more for Charlie. Wouldn't more efficient drilling require more energy? I mean, wouldn't improving geothermal drilling reduce its energy return on investment? I'm not really sure what that means. Charlie, did you want to try it?
Well, you can have absolute efficiency gains. Putting in diamonds in your bit heads. I mean, it costs you something to get the diamonds, and that should be factored in. But I think there's all kinds of ways we can have absolute increases in efficiency. And the thing to me about ERoI, if you can actually measure it in oil at least, is that it's the difference between the increase in efficiency and the decrease caused by going after poor resources, caused by depletion. So it's gives an indication of the balance between those two forces. And if you have enough data, you can do that. And in general, the ERoI for drilling for oil has been going down over decades, and that implies that the reduction in the using up of the best resources, so you have to go after poorer quality resources, the net effect of that is greater than the improvements in technology. But you can only do that by empirically measuring ERoI, and you normally need government resources to do that, and they have been not as good at maintaining the records, at least in the United States, as they used to.
Dan?
Yeah, what I'd like to point, I like to make in regards to the difference between drilling for oil and gas versus geothermal. Geothermal is probably, for all practical purposes, an infinite power source. The oldest geothermal power plant that I know, there's the plant that my dad and his team brought online in 1980. That power plant's been running for the last 45 years. So how do you calculate the ERoI on a power plant where you drilled the wells once and you're gaining energy out of it for 45 years? So a lot of these plants, we don't know how long we're going to pull, how much energy.
Extremely high.
I'm sorry?
It would be extremely high.
Yeah, a lot more than.
Yeah. I mean, I assume there's operations and maintenance costs that you'd have to factor in, but I mean, I always say, if you're so smart, why aren't you rich? If these things work so well, why aren't we doing it instead of chasing after the dregs of the oil? It's not exactly dregs, but see what I'm trying to say. So where is your father's plant?
Well, that's all true what you're saying, Charlie, but you also have to remember about human beings and their propensity to keep the things they already have dragging on. For example, my first presentation from the group, I talked about the fact they have invested $2.3 trillion just in the 130 some odd oil refineries in the United States. They're not just going to drop that and basically pick up a new energy source. Or for example,
well, the cost of changing.
For example, out in Georgia, when they finish up Vogtle, the two Westinghouse reactors, those reactors have a 50-year lifespan. They invested $26 billion. They're not just going to drop that and go with something new.
Well, I mean, if you're talking about energy costs, the new technology is a huge upfront energy cost to do it. And so if the transition, I mean, we don't even know how to do the transition, but let's say we want to make a transition to geothermal, then that would require huge energy investments, even if the payoff would be very large. But and this is Kaplan Perez in Spain has done good modeling of this. So your costs, your initial costs, that's the problem with all these renewables, is that the energy costs or economic costs, they're sort of the same, are up front. And so in the transition, if you're going to build out an infrastructure to equal oil and gas, my God, the infrastructure costs would be enormous.
It's massive. Well, I try to explain people, because they ask me when we're going to do this transition to things like hydrogen or geothermal, and how I explain it to them is simply this. This goes back to what happened in Boise. So we had in the United States and most throughout the world, we encountered an energy crisis back in the 70s, actually two of them, 73 to 74, and then 78. Well, what happened there in Boise is the mayor of Boise took the governor of the state of Idaho up to Warm Springs Avenue. Warm Springs is a place where back in 1890, somebody drilled a water well and started using it to heat his house. And today there's over 300 houses in that neighborhood that are heated by hot water coming out of the ground. Pointed out the truth there in 1980. By 1983, they had drilled their first wells. So today, if you go to Boise, all the buildings, the Capitol buildings, and something like 73,000 houses in the Boise city are all heated with geothermal. But it took an energy crisis to drive them into doing it. So because human beings will sit there and say, well, if it's not a problem, I'm just going to keep using it. I can still buy gasoline. I'm going to keep doing it. I can still buy diesel. I'm going to keep doing it. The nuclear
Well,
power plant is still working, therefore we're going to keep doing it. And that's just how human beings are.
we have that at Klamath Falls, Oregon, too. I live in Oregon.
Yeah.
And so there's some shallow areas that I don't know if they get hot enough to do some of the things that Doone is talking about, but I mean, certainly we would want to exploit the shallow hot areas first. Doone, do you have any idea whether in places like Klamath Falls, Oregon, where there's Oregon Technical College, it's all heated by this hot rocks in hot water. If you drill down not too far there, can you get water that's hot enough to make electricity?
USGS
shallow areas.
The USGS has done a lot of work looking at temperatures throughout the whole of the continent, just like we did in Australia.
Their maps
So
of the
they
United
would have
States,
an understanding about what it would be like at any location.
There are maps in the United States that you can get. Go ahead, Andrew. I'm sorry.
Yeah. Okay. So I just have several housekeeping issues to deal with. I have one persistent YouTuber that has a question, but then after that, we have to sort out who's presenting because we got a limited time here. And I know possibly Charlie, definitely Dan, and possibly Simon wanted to present. So the question. And so what energy source is used to maintain the pressure in EGS and how much energy does it require? And they're still wondering how much water needs to be injected since these are very dry areas.
The current 30 geothermal power plants in the Western United States, the water's at 300 bar pressure.
Okay. And then you need to have pumps to maintain that pressure to keep it going.
Once it's pressurized, it's always pressure. The only time they depressurize it is when they're doing maintenance, and that's once every 10 years.
Okay. Good.
Could I
go ahead?
In an EGS project, there is a sort of a friction through the rock. However, you've got an advantage in that you're pumping cold water down and you're getting hot water back. And so there's a natural thermosiphon, which eliminates that to a certain extent.
Okay. Think about it this way. If you take and build a 1 meter by 1 meter by 1 meter box and you fill it full of water, that's 1 metric ton. And if you can imagine a column of water, something like that, going, 4, 5, 6 kilometers, 12 kilometers in the ocean, that weighs, thousands of metric tons, if not millions of metric tons. So whenever the water hits the bottom, you're talking about millions of metric tons of water pressure on the rock at the bottom of the well. And then whenever the water heats it up, especially if it's especially if you're talking a couple hundred degrees Celsius, the water wants to expand and escape. So you get this natural thermocline. As far as like pumps and stuff like that, all they simply use is they use the heat of the water itself to pressurize it. They use these things called steam generators. It's like a big metal tube, and the steam catchers in the bottom. Of course, whenever water flashes into steam, it expands by 2,000 times, and that's how they pressurize it, by using that fact that the water wants to flash into steam and use that steam to pressurize the well. So they don't use pumps to do it. They use the heat itself to pressurize the well.
Okay, and then the other part of the question they were very persistent on is how much water is used because they're concerned about water use in dry areas.
Well, it could be thousands and millions of water in the actual loop itself, but the power plants use air plants that are greater than 600 megawatts that you require water cooling, and that means you have to put it next to a lake, a river, or the ocean for cooling. But most of these power plants they put out in the desert because we don't have a place where we can do water cooling. But yes, initially when you're building and fracking the wells, you could require thousands of gallons of water to do that. But water is always constantly circulated in and out of the crust, so it's preserved.
Okay, very good. Okay. All right, so I guess Roger's had his hand up, and then we'll sort out about who's doing the presentations in what order. Okay, Roger, go ahead.
Yeah, just very quickly. We've had several of these discussions before, and what Dan was talking about, and Charlie, we mustn't forget the ordinary thermal heat down there. I know we like to focus on electricity, but again, other quoting, my university, Reading in England, has a nice thermal source underneath it. We think it's naturally replenished. So, you know, we need a lot of ordinary thermal heat for our houses, and it's down under our feet. So we love electricity, but we mustn't forget also just the ordinary, normal 100 and 120 centigrade. Thanks, Bob.
All right. So now I want to know who wants to present and how long a time slot they want. Okay, Charlie, Dan, and Simon.
Charlie can go before me. Mine. You can wait
No,
till next time. I'll do it that way.
I can't remember. I can't remember what a month ago I wanted to talk about. So
Okay.
but I would like to say that I don't think I've had my question answered about whether the plasticity of the rock to fill in the holes is gonna Scott's the plans to make a lot of geothermal electricity wells, that if it's hot enough to make electricity, can the well holes stay open and the fracking wells in rock that hot? I've just heard arguments about this, and I thought I was going to get it answered today, but I didn't. Anybody want to answer that?
I can try to give you an answer with what's already been done.
Go ahead.
Okay, go.
The easiest way to answer your question there is I can give you actual examples where we've done it and where things actually work correctly. So it's not a question that's it's already empirical. That's what I'm trying to tell you.
Oh,
but it could be a problem.
No, it's not.
Okay.
It's
Well,
not.
okay. So, like, okay, Dan is going to do a presentation about the subductile transition, kind of working on what Doone was doing.
Well,
how
I mean, you and I talked about that presentation. You had questions back and forth, but
yeah,
I've kind of figured out how I'm going to answer it. I'm going to answer it with, I'm going to show you guys a brochure of a company that I work with that actually drills wells for me. Okay, that I actually pay them to do this kind of stuff. Right?
Okay.
And then I'll go through and show you what's already been built and completed and actually in operation, if that's okay.
Okay, cool. All right. So, and then how long will your presentation?
Let's see, I got about 49 minutes, I think. I could probably do it in 45.
Okay. All right, Simon, I wanted to check in with you because you're muted right now. You got on mute.
Hi everyone. Look, I took most of the time last time, so give the stage to others. I do have stuff to contribute with regard to what I think the Americans are doing, as in what's Trump's plan. I think I've worked out at least part of that. That can wait till next time.
Okay. All right. Okay, Dan. So we'll start with you then.
Okay. Let me see here.
All right.
I gave him the thing with the application templates. Okay.
Just wondering if maybe Simon, you can give us a sneak or there. Okay. I guess Dan's got it now.
Yeah, let me go ahead and just move. So,
okay. Yeah, you should be able to go full screen here.
So this is just a PDF, and I tried to break it up, and I talked to the guys, and they'd rather I just basically show you this PDF. So it says a geothermal solution. So there's a company called Neighbors. They're a driller. They actually build the horizontal drilling and fracking equipment that all of you guys have been hearing about. Their ticker symbol on the New York Stock Exchange is MBR. Okay. They are basically involved in at least 70 of the oil and gas markets throughout the world. They've got a partnership with Saudi Aramco. They're currently doing drilling right now in Kuwait also.
Could you maximize your window, please?
Okay. That good?
Yeah. Yeah, that's good. Thanks.
Okay. So there's a number of these geothermal companies that they've been buying throughout the number of years. And of course, they have been, for example, the 26 California well and New Mexico wells drilled. So products and services. So they build some of the largest drilling equipment that you've ever heard about. For example, all the wells out in the Gulf of Mexico that I was telling you guys about that are 10 kilometers deep. These are the guys that build that drilling equipment. A large rig is this one right here. And it's based on how much steel they can actually lower into the ground. Over 2 million pounds of steel.
Oh, okay. That's the pounds there.
Yeah. Pace M. It's the largest one.
Mhm.
I basically have them. I contract them out to do my drilling. I read that way. I don't have to own the equipment, but you can actually buy the equipment from them.
Mhm.
As far as their drilling technology, of course, here's all the different types of geothermal projects that they're involved in. The one I'm more interested in is supercritical, and that's 10 to 20 kilometers down. 373 is supercritical steam for driving steam turbines or binary geothermal power plants.
A hydrothermal, I see. Mm-hmm.
Right. And that's why I was trying to tell you that what they discovered with drilling these wells that are deeper than 10 kilometers, that underneath that the rock is less dense, it's full of hydrogen and water. And then basically above that is really the rock is a lot denser and much more brittle. And generally what they do when they build these supercritical reservoirs is like building a sort of like a bubble that's under the really hard and brittle rock.
Oh, I see. Are those little fractures within it that we're seeing, those lines?
Right.
And have
Where's
they?
the hydrogen come from?
I'm sorry?
Where's the hydrogen come from?
I don't know. It's my guess it has to do with chemistry, where basically oxygen is reacting with things like magnesium or sodium or whatever, and a byproduct of that chemistry happens to be hydrogen. Lithium, for example, lithium chemical reacts with water from lithium oxide, and hydrogen is a byproduct.
Hard to imagine how lithium will displace hydrogen, but all right.
It has to do with like lithium burns, right? It has a really good affinity for oxygen, and the lithium metal, or for example, sodium metal or potassium metal, all those metals chemically react with water, and some of them are pretty explosive. You've ever seen like potassium metal dropped into a little glass of water or something in chemistry class? But yeah, that's what the thought is. Has to do with chemistry at that level. Direct use hydrothermal, like I said, I'm more interested in supercritical geothermal. And it talks about water being supercritical and it's 220 bars of pressure. Of course, supercritical is injecting fluid, hydraulic simulation, 10 to 20 kilometers. The temperature. And this just shows you some of the tubular running management pressure drilling. I'm more interested at those high temperatures. They have robotic drilling equipment that they use. Drilling equipment. Automation. These are the robotics that they use for handling drill pipe and so forth. At those high temperatures, more than 200 degrees Celsius, it's pretty hazardous for human beings to handle that type. Yeah, handle that type of equipment. Automated pipe handling. Pretty hot.
Mm-hmm.
They got the top drivers.
So the technology is still screwing pipes together is to make drill strings?
Yeah, they still drill pipe together. The robots drill the pipe, screw the pipes together. If you want to know how long it takes them to drill a 12-kilometer well, it's 60 days.
12 kilometer?
12 kilometers, 60 days.
Wow, that is fast.
Yeah. If you want to know what it costs to drill a 12-kilometer well, it's $20 million a well. So if you do a pad of 6 of them, it's $120 million. That's most of the cost of your geothermal power plant right there.
And that's just straight down.
That's short. That's straight. That's going down about 11 kilometers and then horizontally go out to another 2 kilometers. So it's actually 11 kilometers down and 2 kilometers horizontal.
Oh,
so
okay.
It's 13 kilometers with the pipe in the ground.
Mm-hmm.
Now, is this mostly for hydrocarbons?
This is for geothermal. This is a part of the company that they do for geothermal. Yeah. They use in my presentation, I talk about the fact that they use basically the same equipment. The oil and gas industry actually uses the same equipment as the geothermal equipment stuff.
Doone has a question.
Go ahead.
Yeah, this is all theoretical, Dan.
No,
I
it's
mean,
not.
nobody's drilled that deep.
Not theoretical.
Nobody's drilled that deep.
Yes, they have.
In those to those temperatures. The hottest
That's not
well
true,
that's ever been drilled was that one at Krafla in Iceland.
Give me a second here. Give me a second here. You see Electrum sheet right there?
Yeah.
Okay.
Electrum Power Tech.
Okay, that's just blackouts in the grid and stuff I have to deal with in the United States. So this is a geothermal power plant that my dad and his team drilled that did back in 1980.
Mm-hmm.
This talks about horizontal drilling and fracking, the oil and gas business since the 1880s, and how they started doing fracking. They simply would pour nitroglycerin and drop in a stick of dynamite. That's how they'd stimulate the rock. And then when they do horizontal drilling, that was actually back in the 1950s when they developed that. And what the oil and gas business is, you've got a production well, the water and oil come up and they separate out the water and the gas, and then they inject the water and the natural gas back down into the structure. So if you're in the oil and gas business, you're in the geothermal business, and that's from the Department of Conservation there in California, is where the graphics from. Can you see it? Everything's right? Fine?
Yeah,
Andrii?
yeah. I can see it. Once oil has been removed, water is returned to the geographic formation.
I'm just trying to say, if you're in the oil and gas business, you're in the water business.
Oh, okay, yeah.
And this would be, this is EGS, or simply have an injection well and a production well, and you horizontally drill and hydraulically fracture the rocks. It's a lot of the same technology. So, and this is, you were talking about deep wells. So this is in the Guinness Book of World Record. I can send you out the link and see it for yourself. It's a Chavo Z44 well drilled there in Russia, there in Sakhalin Island. The well's 12 kilometers down. There's a horizontal aspect that Andrew and I keep arguing about. We can argue about what that actually is. But it didn't change the fact.
Yeah, the Russians drilled the deepest well.
No, this was done by the Parker Drilling Company, which is a subsidiary of Neighbors. Is who drilled this.
It was just done in Russia.
In Russia, yeah, but that was defeated by this, and I'll
Oh,
so
okay.
this is it's in the Guinness Book of World Records. Exxon Nafgas was the main contractor. Well depth is 12,376 meters. Bottom temperature is 371.28 degrees Celsius, so that's pretty close to supercritical. Has 2 saltwater injection wells, 8 production wells, producing steam and hydrocarbons. They got a 340 megawatt steam turbine that they actually power from the wells, and then they condense the hydrocarbons out from it. I have no idea where they dump the well water, by the way. The drill rig is 52 meters tall. It's 171 feet tall. In the United States, we use about 500 megawatts of electricity per hour. Right, so that's a little 48.
Mm-hmm.
I'm trying to go faster. So this is from the Department of Energy. Basically, it says that we could replace all our base load power in the United States with geothermal if we wanted to. So according to studies, and that's drilling super deep wells. As far as the cost, this is also from the Department of Energy. You look over on the left-hand side, your capacity factor. That the geothermal has the same capacity factor as advanced nuclear. Your realized capex is definitely a lot cheaper than a nuclear power plant. Operation and the maintenance is a lot less than a nuclear power plant.
Mm-hmm.
You've got the price per megawatt is half that of nuclear power. So
yeah, you're basically using the nuclear reactor of the Earth's core, but it's shielded by lots of rock.
yeah, well, you don't have all the cost of the reactor and the nuclear fuel. I mean,
Yeah.
it's basically a coal-fired power plant, but you're circulating water through the crust of the planet.
Mm-hmm.
Right, and then this is the presentation I showed you before. Where I got the wells are 11 kilometers deep, and that's drilled. That's basically where you have just one drill pad. You drill 6 wells in one drill pad, and underground you got 2 injection wells, 1 production well, and it basically forms those huge bubbles I tried to describe at that.
So this is the supercritical
steam, and
okay.
This is what the diagram for the internal power plant looks like. Notice you got the pressurizer, and all that is a big metal tube, and they allow some of the water to flash into steam. We use the pressure of the steam to pressurize the wells to greater than 220 bar, which actually in actual practice about 300 bars, what they pressurize into. Okay,
Mhm.
And this is what one of the ones look like. That's for 110 megawatt turbine.
What's the virtue of pentane?
We use isopentane as the working fluid in the power plant to drive the turbine. We can use a lot higher pressures to actually drive the turbine. This is the largest one we've got in the United States. It's McGinnis Hills. It's in Nevada. It was put online in 2012. So, and that's run by Ormat. So,
And this is those are cooling towers.
those are, yeah, it's just air cooling.
Hmm.
And those tubes you see down there are the heat exchangers, and then the generators are between the heat exchangers.
Hmm.
We figure
Where are the generators?
I'm sorry?
Where are the generators in that picture?
The generators are actually located between those metal tubes to the right. Those long tubes. See where you see like a lime green down there, that between the tubes, that's where the generator is located at.
The lime green. Okay.
Yeah, the right hand side, there's those long metal tubes. And down just a little bit to the left of those metal tubes.
If you go out of full screen mode, you'll be able to move your mouse so we can tell what you're referring to.
There are long metal tubes going in two directions.
Right about here. Right about here is where the generator is located.
Oh, okay. Oh, right over there. Okay, I see it. Okay, those orangish tubes there. Okay, that's the generators.
And that's constantly on, more or less, at 143 megawatts.
Base load, 90% capacity factor, same as nuclear power. We shut them down once every 10 years to do maintenance.
Great.
Why, if you're so smart,
more than 100,000 hours. I'm sorry?
If you're so smart, why aren't you rich? Why don't we have hundreds of these plants?
That is a good question, Charlie.
Okay.
Yeah, we actually, I want to, Charlie, you missed this, but we actually have 17 gigawatts installed, providing 98 terawatt hours a year. It's already, 0.35% of global electricity, and United States is the leader, and it's growing at 3% a year. But it'll probably grow faster as we have more of an energy crunch and there's more motivation, like Dan was saying.
Yeah. Yeah, so anybody who's interested, you can contact, like I said, Electron Power Technology or Tiger Shark Engine Consulting. That's General Stan Osman's company. And generally, we have neighbors. We have them drill the wells, and then we build the power plants on top of them. And whether you have us build your power plant or whether you want to let Ormat do it, Ormat's done quite a number of projects over in Kenya that they're pretty proud of. But those are the power plants we're actually building already. So it's not theory anymore, is what I'm.
Yeah, Kenya's in the top 10 now. Is this okay? There's more presentation. Okay, go ahead.
No, that's all I had. I tried to be quick about it, but
okay,
well, but yeah, there's a lot of people that think it's theoretical. I was like, well, there's a lot of theory we've been building, but there's already 30 of them out west. There's actually 7 of them down in the Salton Sea. Warren Buffett owns 3 of them, so it's not like the billionaire class doesn't know about them. Warren Buffett's trying to extract lithium out of the 3 geothermal power plants he has. He's trying to turn it into another money maker for him. So, as to what Berkshire Hathaway does with their power plants, I don't really know. I know that Ormat runs those 4 that they got down the Salton Sea for the California ISO and providing the power. And of course, they've got power plants. I think it's Mammoth and of course up to Steamboat. But you'll find most of these power plants. I think there's probably at least 20 of them. They're in the state of Nevada. If you want to know how that happened, basically, we've got a place where you can't build any other type of power plant, so they allowed them to be built there. But the big public utilities, they truly have a monopoly on their rate, on their customer base. So,
where do you get the fracking water?
That's a good question. It usually has to be trucked in. But that fracking water stays in the well. We never release it. It goes in there and stays in there. We use that water to frack the wells.
Yeah, and then it recirculates.
Charlie, it stays in there all the time.
Here, I can re-show what I was showing earlier about the current state of it globally. So installed capacity 17 gigawatts, producing 98 terawatts globally. Here in Asia, there's 30 terawatt hours of production. In North America, 20. Central America, 8. Well, you can see the numbers there. Top production countries, United States has 4 terawatt hours. Indonesia, Philippines, and then see that there's Kenya is number 6. So Ormat or whoever does have something to be proud of over there. 10-year growth rate over the last 10 years, it's grown at 3% a year. And then it is notable. There's geothermal heat. They have, what do you call it? It's become accessible to regular people, and so that's growing.
You can definitely build what we call district heating. You can use it to heat about any town that you want to. That's easy to do. If anybody's interested, take a trip out to Boise. They have a museum there. You can go through it. They'll basically give you a class on how to build your own geothermal public utility. So that's the easiest thing I can describe, how to actually structurally build a public utility that just does district heating. You want to do power plant, there's a little bit more expertise, but we can handle it. Put in there the link on the Guinness Book of World Records on that I showed you guys.
So if you had a map of the United States with the depth you would have to go to get enough heat to make electricity.
What we've done, Charlie, is we just standardize on the 11 kilometers, and just that way we can fix our costs at 11 kilometers. We know that'll work anywhere in the United States.
11 kilometers works anywhere in the U.S.
11 kilometers worth of 16-inch casing in the ground. That's what it costs.
Yeah.
If it gets over 400 degrees, we just stop drilling. We said, okay, that's good enough, and I saved a ton of money in pipe. But basically, when we go in, we standardize on 11 kilometer deep, and then of course horizontally 2 kilometers, so that's 13 kilometers worth of steel pipe in the ground times 6. So that way it's standardized, and we end up spending less money. Hey, we charge the customer that much less. Hey, we didn't have to spend all this pipe.
But it's about $20 million.
$20 million a well.
And then you need several.
6 of them is 120. That would give you 240 megawatts worth of let me think about that. It'd be 300 megawatts worth of generating capacity.
Yeah. So I just wanted to check on the IEA projections. It says with large cost reductions could be 15% of global electricity by 2050, 800 gigawatts of thermal power capacity, and 6,000 terawatts. So that's kind of like their optimistic scenario. And
yeah, that basically means what people allow us to do. I mean, I showed you that cost reduction. When it comes to base load, that geothermal power plant, its base load, it's even competitive with solar and wind turbines. So there's a lot of I've had to actually deal with. I've got players out there that really don't want me to build power plants in the eastern part of the United States. They really don't.
So that's about a third of a nuclear standard nuclear plant.
Yeah.
For $600 million, you can build a nuclear plant equivalent.
Yeah. Well,
you want to present it that way.
Here's another way of looking at it. Here's another way of looking at that. I'm not saying this a little strangely. There's some states that have actually got regulations on geothermal power plants. It actually makes it harder to build a plant. But there's a bunch of these states that just don't have any regulations. What the regulations are is, hey, I drilled a water well, because that's really all these are, just water wells. In those states, it only takes me 24 months to build a plant, 6 months for permitting, 18 months to build the plant.
Well, I think you ought to make an advertisement that shows a nuclear plant and the stats.
Okay, so
the same amount of power from your thing.
I'm going to answer that question, and it has to do with because I've actually talked to the people. So I actually know the guy, the director of nuclear power at the Department of Energy. I also talked to some of the regulators there in Georgia. So a quote from the regulators in Georgia, and that is, when it comes to nuclear power plants, enough was the term that they use. So you're not going to get another nuclear power plant in the state of Georgia. Unfortunately, the other 49 states are going to follow the state of Georgia. So the odds of us getting another power plant built is probably pretty low, unless the federal government comes in and ponies up a lot of the money. But a lot of the public utilities won't be building another nuclear power plant. That Vogel plant, $36 billion it took to build it. That project bankrupted George Westinghouse, the company. It bankrupted them. Another thing most people don't realize is a couple of years ago, I think it was in 2019, General Electric went bankrupt. So understand that's impacting a lot of the thinking in the utility business. So no, they're not going to be building a nuclear power plant anytime soon. And I've also tried to explain to people, if you're going to build a new design reactor like TerraPower or whatever, you got to go through design testing. And that means you're going to show up to Idaho National Engineering Lab, build your reactor out there. You're going to go through 10 years worth of testing, and deal with the national, I can't think of the name of that single place. But the point is, it's a national laboratory for nuclear power that you're going to go through to basically get your design approved. And then when it comes to building your plant, so you're talking 26 years in the future before you might even see a small modular reactor. So my point is that's not going to come anytime soon. And also think about how many election cycles are going to go on between now and then too. So the odds are.
You need to make an advertisement, full page ad, with the nuclear power plant on one side and your plant on the other, and say, if you want 1,000 megawatts of power, and here are your options, and maybe another one of wind turbines, I don't know, and just put those. So you're saying you can do it for $600 million versus the nuclear of how much?
No, nuclear is a lot more than $600 million, Scott.
No, yours is for 1,000 megawatts, something like six.
I can't build 1,000 megawatt geothermal power plant with the drilling technology we have. I can build these 150 megawatt. The twin plant I was sitting there showing you is 300 megawatts total. But when you have power plants that are greater than 600 megawatts, you have to have water cooling. That means the power plant's located next to the river.
No, not one power plant. You build all right. 3 of them.
Okay.
Yes.
Yeah. So you'd have a grid of these smaller ones, and then
right.
It could work.
What we're actually pushing for, Andrew, because if you notice the power plant itself, it's not any taller than 2 stories. You can put a fence around. A lot of communities, they put trees around it, so you don't even know it's there. The other thing is we could co-produce district heating for producing steam and heating throughout town. So the best place to put one of these is actually in your town, because you can put it inside of a Walmart parking lot and you won't even know it's there. And on top of that, you can provide steam for heating buildings and houses and stuff like that. So it's a different way of looking at the power grid.
Okay, and I was wondering, you said you were talking to the Newberry people, the town there?
When I talk to the people, I've got family that lives there in Bend, Oregon, right? But when I talk to them, because you have the people trying to build a power plant up the Newberry volcano, the people there in Bend don't want that area developed, Andre. They want to keep it the way it is. It's a fishing, hunting, backpacking, that kind of thing. What they would rather have is actually the power plant right there in town to do exactly what I'm talking about.
Okay. So the power plant in the town, how much would it cost them?
It's $1 a watt. So if you wanted 150 megawatts, it'd be $150 million.
Oh, okay. All right. And that, okay. So I think that there was one more question for you, Dan. What do you think about millimeter wave drilling using gyrotrons?
Well, the problem is drilling deep like that, the rock becomes plastic and it tries to close in the hole. So I'm not quite sure how you would use a microwave device to basically microwave through drill mud. So I mean, when we pump mud down through the drill bit, it started to clean out the rock chips and stuff are up around the drill bit, but it also provides cooling and keeps the well bore pressurized until we can drive in the casing. So I know there's that gentleman that's down in Texas that's got this klystron or some kind of a microwave tube to try to blast away the rock. But the problem is at those levels, you have to pressurize the well to keep the rock from closing in on the borehole. So I'm not quite sure how it'd work at the depths that we're talking about for building power plants, which is those 10-kilometer depths.
Okay.
How deep do you worry about the holes closing in?
Well, anything past 10 kilometers, the rock's plastic.
Well, you're talking about putting yours in at 11 kilometers.
Yeah, we drill it, drive in the casing, drill it, drive in the casing. If you want to know what the span is, we'll,
Yeah.
So the
we'll drill about
casing
12
keeps
we'll drill about 12 feet and
Yes.
drive in the casing. Is what we do.
And from what from talking to the other EGS researchers and the deep heat and stuff, they're actually saying it's closer to 4 kilometers. Below 4 kilometers, it becomes very plastic, and its EGS isn't really viable. But possibly in that what we were seeing, that ductile zone, and that Dan is talking to, that supercritical zone, it might work. So we actually do have some time for Simon, if you wanted to.
Do you have to clean out the pipes?
They pump drill mud down through the drill pipe, goes down through the bit, and then comes up around it and comes back to the surface.
Yeah, but do you have to service them? Do you have to
as far as
service the hole?
what we do is when we pump in the water to frack it, mud will come out, and we get some wastewater from that. When it runs clear, then we turn it off, and then we hook it up to the heat exchanger.
And then it lasts forever, or for a long
Well,
time.
I mean, Rafter's been there running for 45 years, so I guess. Don't know. We'll find out, Charlie. But 45 years is a pretty good track record.
Yep.
Yeah. All right. I don't know. Simon's busy with something right now. Okay. Let's
He's
see.
trying to get ready to give his presentation.
Oh, okay. Okay. Let's see if there's some more questions for you guys. Doone, go ahead, Doone.
I'm just getting started. So hang on,
Okay.
let's put the camera over here then. There you go.
Okay.
I got, there you go. How's
Okay.
that?
Good. We can see you.
Okay.
Can I just
so
say something?
Oh, okay.
please.
Yeah, about they're about hydrogen deep in the rocks. There are locations where hydrogen is produced. It's generally where iron-bearing rocks are actually oxidizing, and then hydrogen is produced as a result of that oxidation of
They've got that
iron.
great place up in Canada. I've been hearing a lot of reports about. It's pretty impressive. Yeah.
Yeah.
Is it
There's
enough
another
hydrogen
school
to exploit?
Well, they're looking at it. Yeah. Yep. There was also another study that was done where they were talking about abiotic oil, and there were a couple of 6-kilometer wells drilled in Sweden. This was back, I don't know, in the 80s, I think. And anyway, they didn't find, they were looking for methane. They didn't find any methane whatsoever. The only gas they found there was helium, which was derived from radioactive decay of uranium.
All right. Are we ready for Simon, guys?
Sure.
Yeah.
Okay.
Right.
Go ahead. Take it away.
Everyone's had their chance, yeah? So I took the stage too long last time. Right, okay. So what I've got to contribute now is I work in a field called mineral intelligence. I work for the Finnish government. I've been given a couple of assignments lately to go off and sort of work stuff. I can't tell you what they are, but what I can tell you is what I think.
Okay.
So I'm not going to tell you directly about the assignments, but what I am going to tell you is I think I've worked out what the Chinese plan is, and I think I've worked out what the American plan now is, which is, perhaps useful. And this is based on a couple of things. First, I was given an assignment to go off and do. That assignment, when I did it, the juice wasn't worth the squeeze. As in, what everyone was panicking about, blah, 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 wasn't quite right. So something was off. So something else is going on with what I was told. Then, in an unrelated matter, I'm in meetings with banking professionals. And there's a few things that they were a bit touchy about and didn't want to talk about, in particular in the last couple of weeks, in a runabout, wave your arms, scream and shout kind of way. So what I'm saying is I'm piecing these pieces of information together, and I've now put together what I think is happening. Now, so let me share my screen.
Okay, sure.
Yeah, hang on. So entire screen.
Yeah.
Do it. Okay. I keep getting hacked, by the way. If things start going wrong,
Okay.
yeah. All right. So this is the model that I'm actually sort of piecing together with regard to we all see this, right? We've all the people in this call will probably understand this a lot better than the people I'm presenting it to. Right. So we've got the idea is the system is normal. By the way, are you seeing this?
Yeah. System normal, the invisible 1,000 cuts.
Okay, so things have been going slightly sideways for decades, but we think it's fine. Then we get to a certain point where the system works, but there are visible signs of stress, the visible 1,000 cuts. And I've got January 2005 when that starts.
Mm-hmm.
Then we get to 2019, and then we start seeing some serious things breaking. Like, you remember the repo crisis? Right, so there's a lot of business that we saw internationally at the time, and for the last couple of years, COVID, the gift that keeps on giving, perfect cover. And then we've got everything comes apart in multiple sectors all at once, to the point where there's so much news coming in, we don't have time to process it all. In fact, we saw a bit of that tonight, with lots of people want to present stuff. Right, so old systems get wiped out and new ones will form. And so then you have an adjustment, new structures coming in, and there's an adjustment, and then you've got a new equilibrium, whatever that is. Right, so, and that's the model that we're, I'm putting forward. All nation states, large corporations, and people like us, we're all preparing for this point. This is the prepper community at different scales. We all consider it to be inevitable. So what that means is, how can we position ourselves in the new system, given the old system is obsolete and irrelevant? If a crash is coming, it's all about what do we do with that crash and how do we position ourselves on the other side of that crash. So it's not about maintaining the status quo, and it never has been. So the large players who play the long game, they don't care about market meltdowns or debt default or peak oil. So they're jockeying for position, and they use these things as a tool, especially if they happen to have influence of when things can happen. And so it's timing. So, okay, so I've presented this before, so I'll step through it. So I presented before the idea of the China plan.
Mm-hmm. Yeah.
Now the Western way of doing things, which is actually British, is like chess. We're going to take out the enemy king, like a decapitation strike. That's how.
Like in Venezuela.
Like a what?
Like in Venezuela.
Yeah. Well, funny you should mention that. It's like that's how we're wired. The Chinese, in particular the historical Chinese, think in terms of the game of Go, where they quietly take over territory, and they like to have the warfare happen in a way where their target has even no idea it's happening. And so then there's the question is, well, what's everyone else doing? And the dark horse in all this is India. That's a story for another day. Okay. Right, so and this bit in red, what might we do about it? And so I read these two books. I read a whole series of books, but it was the combination of these two books that actually helped me put together the China plan. They, long story short, they want long-term, full-spectrum global domination through control of the industrial value chain in all its forms by 2049, which happens to be the 100-year anniversary of when Mao took power in 1949.
Oh, right. Mm-hmm.
That is, if you want to do business, if you want to buy anything industrial at all, you will do business with the Chinese in some form. We've been through this before. This is their strategy. They're quietly taking over everything in the background while they're convincing us to look at other things.
Mm-hmm.
The study of history, like what was Mao really up to, that's actually very interesting. And what are they doing now? Now, we've been through this before. Okay, this is the American plan. Okay. So the American plan, I won't tell you, well, we've seen a lot of interest in America. It's all about Canada. It's the cartels in Mexico. It's Greenland. It's Venezuela. It's the Panama Canal. Right. So this is the Technate. Mm-hmm. Now let's go through that. I'm going to come back to this.
Who came up with it?
Say again?
Who came up with it?
Okay, so this was developed in the 1940s by the Technocracy movement.
Okay.
Right, and I'll go through who they are in a sec. I'm going to come back to this map, but what we're seeing here is the plan.
Good.
So to put this in context, we're here are the geopolitical actions. So put them together. So we happen to be seeing Greenland, Canada, United States, Mexico, Central America, Panama, Venezuela, and parts of Colombia. This is what it's all about. So this is oil and gas reservoirs. The stuff in Venezuela is, you know, the big reserves they've got. It's all the heavy oil, and that heavy oil needs the refineries in America to do their thing. So the Monroe Doctrine, 1823. But now, at its core, was declared that the United States would view any European attempts to colonize or interfere in the affairs of nations as unacceptable. A case can be made that the American Civil War was created by banking interests within Europe to try and destabilize the United States, and it was successful. And so they basically sort of leave us alone, blah, blah, blah. And there was a non-interference. We won't interfere with you, and you won't interfere with us, which turned out to be bollocks. So what this means is the United States says, well, we're not going to interfere with anyone. When they actually got involved with World War I and later World War II, was a fundamental change in direction of the Monroe Doctrine. And now they're trying to return to this. For those who are interested, please have a look at this document, National Security Strategy of November 2025. What does it say? Core philosophy, America first. Realism rejects global hegemony and prioritizes sovereignty, economic security, yada, yada, yada. They're reformatting their empire. Priorities, Western Hemisphere first. Someone put up a meme where it's basically got North and South America, put it, Trump, a big circle around China and Southeast Asia, Z and XI, and then Russia and Europe was Putin.
Yeah.
And that's actually, everyone's going after their bottlenecks. Globalization's breaking down. I see it as a function of peak oil. Even though peak oil has been surpassed, the November 2018 localized peak has been surpassed, but we are still having a fragility of it. So they're shifting military resources away from Europe and away from China. Their plan, it seems, they want to move the semiconductor industry of Taiwan to the United States, after which point they'll just leave China do its thing. They plan to confront China in Africa.
I think I wanted to add that I think that historically, when people look at it, they will see peak oil as the net energy, and it'll be like in 2014.
Something like that, yeah. So now it's been flagged as mass migration is a major external threat. This is actually what's happened to Europe. The George Soros actions in Europe to actually sort of destabilize Europe with lots of mass migration is the same strategy. And economic security. So warfare is now moved into the economic sector. And regional approaches. Europe, well, you're on your own. Yeah, right. Yeah. Civilizational erasure is what they think is happening, and calls the halting of NATO. I suspect there's under the table deals with Russia, China. So they want to contain Chinese influence, but I suspect they're going to cede control of certain parts of the territory. Indo-Pacific, while important for maritime security, is no longer a priority. They're going to go more about domestic. And strength through military deterrence, coercive transactional diplomacy, gunboat diplomacy, based on material interests rather than value promotion, and demanding that allies spend significantly more on their own defense. Okay, so where did this come from? So this is technocracy.
Okay.
So this was a controversial social movement that appeared in the early 20th century during the Great Depressions. This is actually Marion King, who was actually one of the people who proposed it. So technocracy was coined the rule of the people made effective through the agency of their servants, scientists, and engineers. And so the intellectual foundation and everything. And so Marion King Hubbard and Howard Scott founded Technocracy in 1932 and proposed that money be replaced by energy certificates. So the economic system, replacing the price system with energy-based metrics. Integration, merging Canada, Greenland, Mexico, the United States, parts of Central America into a single continental unit called the Technate. scientific management, production distribution would be managed scientifically based on efficiency and calculations and market forces, and reduce work through automation. No place for traditional politics. Decisions made purely on a technical engineering grounds. So if you look at Elon Musk's grandfather was part of this group who found this.
Yes, yeah, that's why he left Canada for South Africa.
Right. So now this all sounds all very nice, but what metric of success are they working towards? We all think, let's have a group hug, quality of society and everything, but really it's actually running like a mafia oligarch where, let's collect wealth and power. And so, anyway, so what's very interesting is this is what they proposed in 1932 or 33 or something like that, where industrial technology development will increase to the point where people won't have to work very much anymore, but industrial production will increase. And this didn't happen for decades, but it's starting to happen now, with the AI robotic revolution. So, anyway, so it didn't work. Yeah, you're saying?
Well, we're very productive, but it's just people are working longer than ever now.
Yeah.
So it kind of it didn't distribute because it gets concentrated in the hands of capital.
Right. So okay. So what we're seeing now, this is the formula, the map when you put the pieces together. So what we're seeing now is the Great Reset, which is hearing all over the Western world. So convince us it's necessary, probably in conjunction with some sort of false flag, like some sort of information bomb, like cyber attack. Then we're going to a cryptocurrency of some form, not Bitcoin, but something like Bitcoin that's controlled from a central point.
Like CDBC.
Something like that. Yeah. Oh, gee, someone write that down.
Yeah.
Didn't see that coming at all.
Central bank digital currency.
Right. Social credit system that's Sesame in China is now in Vietnam. And they're trialing it in parts of Australia too. And so I think that's coming for everywhere. Environmental social management, ESG, this is actually what will be allowed. This will be the coercion of what's allowed, and the surveillance state. So digital privacy is gone. In conjunction with who owns what. So if anything associated with debt, like a mortgage or a car loan or anything like that, the bank's just going to foreclose on it, and they will own the stuff. And so technocracy is, you talk to people in the United States, they're not so worried about Trump. They are worried about Emperor Musk.
Oh, right, Musk.
In the background, like, as the economic system, but to what form? And so transhumanism is actually the stage after that, where we're starting to merge human beings with technology. Right, so back to this. So this is the plan for the United States. They're withdrawing from the idea of a global empire into a more regional one. But within that regional one, they want a different kind of power and control structure. The form of what money is will change. I also am seeing and hearing quite a lot where the United States is reforming itself to build its own industrial infrastructure. After the failure of the Trans-Pacific Partnership, or TTP, TTIP, TISA, 3 agreements between the governments of the world and the corporations of the world, which was basically to cut out the BRICS economies. It was supposed to be the replacement of the petrodollar. It failed when WikiLeaks leaked it to the European Parliament, and the Europeans realized they were being screwed. And so the whole thing just fell over. So then this idea of the Monroe Doctrine came back, and that's politics. Everyone we've been seeing for politics for the last 20 years is theatre. Maybe it's always been theatre, where the Biden campaign, Build Back Better. It's the same thing. Build the American infrastructure up again after losing it over the last couple of decades. And Trump's Make America Great Again is actually the same basic form. Rebuild the American industrial infrastructure to be internally reliant. They don't want to be reliant on anything at all outside American borders, in the medium to long term. And so while influence in the world is waning, which it is, with what power they've got left, this is what they're doing to organize themselves. So the Chinese have their plan where they want control of everything. The Americans have got their plan, which is they want control of this patch, which will be a staging platform for the next year or after that. Europe had a plan, but now we're talking in circles and can't agree on a color of an orange. So there's the BRICS economies. They've got a plan. Once the BRICS economies were formed, I believe, to get out from under the petrodollar American petrodollar empire that's based in London. Once the Anglosphere has been dealt with, the BRICS economies, I believe, will go to war with each other. China and India in particular. Russia will have the long-term problem of how do they avoid being absorbed by the Chinese. The Chinese have a whole series of problems with their internal, a series of internal domestic issues, some of which they'll probably deal with, but some of them they probably won't. So it's going to be one big old mess. Anyway, that's it from me.
Cool. Well, I wanted to add a little bit more context to Technocracy in terms of that the Soviet Union was an example of a they were called communist, but really they were a technocracy where they had 5-year plans and everything was based on, planning out the next thing and things like that.
Yeah. So where that analysis came from was me being asked to do things or told a series of things that didn't make sense. And because people like this group, for 20 years, I've been looking at alternative information. Mm-hmm. And as we understand, it's real information and it's just a viewpoint. And I was able to start assembling a picture that what the leadership around me here in Europe thinks is happening, or at least what they'll admit in public, is 14-carat horseshit.
Oh, okay.
They just don't. They either don't know or they do know, and they're telling us to do something else in a way to keep us occupied.
I hear you. Yeah, it does seem to be quite a lot of denial or something that looks like it. Yeah, and then so I also wanted to give the context. So of the other Technocracy, actually Mark Carney, when I get the AIs to analyze, his speaking patterns and his policies, they always pin him as a technocrat.
Yep.
So, yeah, and then China.
All sounds like 1984 to me.
So 1984 is a management strategy. And see, it's a stepping stone. It starts with Animal Farm, then it goes to 1984, then it goes to Brave New World. Then it goes to the French Revolution.
Well, hopefully not. I mean, that was really bad.
So it's the French Revolution, when it happened, we ended up just replacing the same things, and the oligarch just changed form. Yeah. But when you go through history, Mao, where did he get his ideas from? Oh, he looked at the Stalin and the Lenin system. Where did Lenin get his ideas from? Oh, the Reign of Terror from Robespierre and the French Revolution. Everyone looks at history and goes, "Hey, that was a good idea. Let's try that again." Dumbasses. Anyway, so I've got my own ideas.
Trump is just looking at the Italian brown shirts and using their game plan.
So
the other thing, Simon, too, if you're talking about the French Revolution, had to do with the net yacht. That was a paper currency. They learned something from John Law here in America during the things he did in Louisiana and brought it to France. They started printing paper money to pay for their bills, and inflation went through the roof inside of France before that's all the things that led up to the revolution. So you're going to see the same thing happening with the debt levels we're seeing now. That's just another way of printing money to pay for your bills.
But what's apparent to me is all of these things, all of these plans that they think, including every conspiracy theory you've ever heard of, is a management plan for a situation that doesn't have to be. The rules can be changed usually by some sort of technology, or humanity at large won't go along with it and just wants to do something else. Right, so your geothermal technology or the MSR technology or whatever, it's energy and it's high quality energy, and it can be managed locally at a small scale. That changes the rules. That can't be controlled anymore, and we've all got it. So what that does is, while they want us to believe, the oligarchs, want us to believe that this is the way things are going. In fact, this is why I believe the conspiracy theory movement was allowed to exist, was to actually educate the rest of the public on the formula they want to roll out. Fear is your God, kneel and pray. We're all screwed. This is what's going to happen, and it's all going to be terrible. But the moment someone puts their hand up, you've probably experienced this, Dan. I'm going to put my hand up and say, I've got a positive solution. Kill that guy. Stop him. Shut him up.
Yes, I have. I've been in management meetings where we're talking about grid strategy and stuff, and I pull up graphs and charts of the Department of Energy, and I'm like, guys, you got plenty of power. Why are you complaining about this energy issue that doesn't obviously exist? Next thing I know, I'm being escorted out in the hallway and being surrounded by 6 people. So, yeah, God forbid that you would actually point out the truth.
Yeah. So, but here's the thing: if we don't play along with it, what was it? The script says we're supposed to lose. Fuck the script. Let's do our own thing.
Yeah. Very good. Yeah, and then, well, there's also, the rural transition option of letting people have land and things like that. So there's many possible positive outcomes that we can look forward to. And the main thing is to keep on presenting those positive ideas that you're getting, and keep, as they say, fighting the good fight. But I would say maybe promoting the good piece.
Well, the thing is, there's some good things out there, and I don't know enough about Canada, but for example, like on the power grid stuff, most people in the United States don't understand the rules that have to do with what we call co-ops. And what a co-op is where a town literally that you can take control of your own energy infrastructure and produce all your energy, and as long as you don't attach to the power grid, that therefore it doesn't involve the something like the FERC, meaning is central control there in Washington, D.C. Most people don't realize that all those laws exist to the benefit of a town. So actually, a lot of this stuff, a lot of us can actually opt out of it at the town level, at the county level, if we actually understand the laws and how things were put together. Some of the large centrally controlled systems were basically done with us actually volunteering, they get involved in those things, not realizing that originally when they formed it, they gave some kind of an option to get out of it to keep people from resisting against the things they were putting together. You need to do your research is what I'm telling you.
Yeah, and you know how money is made through basically, well, fiat is that it is accepted for taxes. And so actually a town or a municipality, at least in Canada, is allowed to have property tax vouchers. So you could make your own currency by saying, okay, we will pay you this, and then you can pay your property tax with this. And so there's lots of opportunities.
That similar thing, we have 16 states that have actually taken some kind of they have these leaf gold notes that you can use that to pay for your property taxes in 16 states. If you guys haven't seen it, so basically it looks like a note. You'll say Florida on it or Nevada, whatever, but it's finally pressed a couple of grams of gold. But that's one of those legal loopholes they put in the Constitution. And now we've got 16 states that legally you can use that to pay your taxes. And technically, since it's not dollars, it's not under the IRS, but yeah, you can use it to pay your local state property taxes with it. So it's one of those little loopholes that the states are kind of sensing something's not wrong and taking things into their own hands.
Oh, Simon, I was wondering if there's been any updates about the Norway stuff.
Yes. So what's been going on there? So there is a test that's in progress of a thorium molten salt system in Switzerland. That's in progress. The Norwegian guys are slowly getting organized. There is several things happening in parallel streams. There is the test to actually get is molten salt real? Let's talk about it, because there's still the industry interest groups that want this to go away are trying very hard to bury it. Because if it's proven to be real, almost all of the existing nuclear industry is now going to be obsolete. And then you've got all the other energy systems will be under pressure too. There are a few people that are not very happy about that. Right, so there's a lot of pressure there. Once the technology is real, it does work, then we have a different conversation. So then we've got legislation that is in the process of being changed in Sweden and in Norway. Conversations are happening, but we've yet to actually get any actual legislation, but it is being discussed. Right, in parallel with that, there's the permitting cycle. To get permits on the ground, you need to have things like background radiation stuff, measurements in selected sites and value chains looked at, and risk mitigation analysis. All that stuff needs to be done. That is yet to start properly, but it's been informally started.
You need a concrete factory. Lots of concrete. That solves that problem.
And so, yeah, so it's happening with several things running parallel. What's interesting is the system that's in China that's been selling commercial power since 2022. Someone told me this, and this actually makes sense based on. I spoke to some people when I was in Hong Kong, and one of them was the governor of one of the provinces. And he said something that makes sense now if this was true, but that reactor in the Gobi Desert was actually partially facilitated and paid for by the US Navy.
Ah.
What? You guys are at war, or are you? Yeah, yeah. Really? What? Yeah. So it's running. The Norwegian project is still a thing, but it might be eclipsed by what's happening in Southeast Asia with the same technology. All over Southeast Asia, the entire region's ready to go. They are all watching the test in Switzerland. If it's successful, they're going to go for it like a herd of refugees after a food truck. It's going to get ugly.
Wow.
There's and they're also looking at, there's about 15 at last count, organizations around the world that had the capability to make an MSR. Copenhagen happens to be the most advanced, but they're not the only one. And so the Asian groups, especially mining, like how do you actually run an asset like a mine that happens to have like a 300 megawatt power consumption in a remote area like Indonesia or New Guinea? Like how do you do that? You're not going to do that with solar panels. At the moment, it's gas or coal or diesel. And so if you're not allowed to use those three, what are your options? And so this is what they are. Incidentally, the Telfer mine in Western Australia were looking at drilling a deep geothermal hole about 10 years ago, and it's all gone quiet. They won't tell me what happened.
Oh.
But yeah, anyway, so just to say it is happening. I suspect it's about to get very, very messy.
Interesting.
The price of success, it's going to get messy.
All right. Yes. Thank you. All right. So we have to round up now. Any kind of closing remarks or questions before? And
yes.
Okay.
Yeah. Look in the chat. I put the link that the Guinness Book World Record on that in that well, so that'll help out the folks that are.
Guinness.
So, yeah, it's in the Guinness Book World Records.
Here, I'll put it in the YouTube chat as well.
Yeah. Mm-hmm. It's one of those things Andrew and I keep arguing about. And I keep telling them, I said, well, it's still in the Guinness Book of World Records. They haven't changed it. So if you can give good enough evidence that they actually didn't do it, they'll probably believe you, but whatever.
So what I would add, what's been seeing in the last couple of weeks, the Basel III banking accord has finally become enforceable.
Yep.
Now that was developed after the 2008 GFC crash.
2019 when they passed that.
So it was past that, but they've been umming and ahhing and faffing about and wringing their hands and
turning gold into a tier one asset. The United States is having a cow. Yeah.
Right. So here's the problem. they can't sell paper, gold, and silver. And
Yep.
as of January 1st, 2026, it went live and was enforceable. And everyone who is involved with paper assets shit the bed, which is
Yep.
why we're seeing what we're seeing in the silver and gold market. Then we had
today alone, there's a $15 swing just in the price of silver, Simon, just in silver today. Yeah.
And so that's why. And then they had like the plunge protection team stepped in to try and so there was a manipulative action to try and gain control. I don't think it's worked. And now we've got shortages again. Silver production peaked in the year 2020. Right. So hang on. And there's a bit of feedback there.
Yeah,
Okay.
I muted Charlie. Yeah, okay.
Yeah. Anyway, so what I'm just saying is the stuff we've been looking at. Oh, Charlie, you had your hand up.
I'd just like to make an announcement. I'm going to send out something to all of you. We have a new journal situation, and I am seeking manuscripts of the nature of things we talk about. So I'm going to send it to everybody. If you don't want to be on the send list, then you can ask to be removed, or if you got specifics you want to ask me, then let me know. So,
all right. Well, I've got some action for you, Charlie. Anyway, what I was saying there before is the stuff that we've been talking about for years is now structurally happening. Hang on to your hat. Don't panic.
Mm-hmm. Yeah, definitely. We're seeing a lot of movement in the market and the finances. So I wanted to another householding thing. So next month, I wanted to give the floor to John Peach because he said he had a follow-up, and he's got a energy rate of return or something else. But then does anyone else want to also add in? Because I don't think he's going to take up the whole time. Or we could see when it goes. Let me just double check the calendar here. March 2026. So Thursday the 5th of that is March 2026. Would that work for everybody here?
I'm in a conference then, but just proceed without me. No,
okay.
Proceed without me. Fine.
Okay. All right. Well, all right. I think we'll finalize the date a little later because I still have to ask John anyways. Okay. Anything else? There was a question from Wenceslas in the chat here. I don't know if you guys wanted to check it out. Something about the French and cryptocurrency. But otherwise, and if Jean Le Herrera have presented, okay, yeah, okay. So I think, okay, who wants to do the closing remarks? Doone, you started us. So how about you give us some closing remarks here?
Well, all I can say is that deep geothermal hasn't been proven, and we need support somehow, financial support to one way or another, whether it be Dan's project or somewhere else, to actually drill down to the depths that we're talking about in an entirely new kind of geothermal process.
I would call it ultra deep, personally, just to
could be, yeah,
because deep is kind of has its own connotations that is proven, and like I said, it's already producing almost 0.5% of the world's electricity. Okay, so as I found you, I leave you in the infinite love and infinite light of the infinite creator within you and all around you, my friends. That go forth therefore rejoicing in the infinite power and infinite peace. Okay. I've ended the stream.